Hi, everyone. Thanks for tuning in to the Printed Circuit Podcast, where we discuss trends, challenges, and opportunities across the printed circuit engineering industry. I'm your host, Steph Chavez. In this episode, we'll focus on power integrity, specifically designing PDNs, or power distribution networks. I'm extremely excited about this specific episode because here to join me in this discussion is my dear friend and one of today's industry leaders, Dan Beeker. Thanks for being here, Dan.
Oh, you're welcome, Steph. It's a great honor to be part of this, and I'm excited to talk about one of my favorite subjects, which is power distribution. It's the foundation of every design, and if you don't get it right, you pay the price.
Dan, before we get into the thick of it here, can you give the audience a bit about your background and all that you bring to the table? Because Lord knows you bring a hell of a lot to the table.
I've been with Motorola Freescale NXP since 1980. I started out in the microsystems development operation where they did in-circuit emulators, working on 6800 microprocessors, and worked my way through the food chain into high-end in-circuit emulators for 68000, 68020, and then moved to the field as an applications engineer in 1987. I was a dyed-in-the-wool circuit guy for more than 25 years of my career, until the fatal day that I went to PCB West and took a 2-day class by our great friend Richard Hartley. 5 minutes into his class, I knew that everything I'd ever designed worked by accident rather than by purpose. And I remember thinking that I sure hope my boss doesn't figure this out, because I had never thought about energy from the perspective that Rick was trying to talk about, that it was fields and they were moving in spaces, and I needed to worry about those spaces. And from that class with Rick, I went on a mission to learn all there was to know about signal integrity and EMC and PCB design, and more importantly, fields. Through that desire for learning, which included multiple visits to PCB West, I've been to almost everyone except 1 year where I couldn't come. And I met Ralph Morrison. Ralph and I started an engagement where he obviously knew how things worked. Ralph was a physicist. So he came to Detroit. I brought him to teach classes to my customers, because my mission wasn't for myself. It was finding ways for customers to be able to create products that were passing EMC. And it just wasn't happening. We'd hired consultants with very little luck on success. They wanted to add a lot of cost to the modules and with no guarantees. So listening to Ralph speak really gave me some new direction. And through that relationship that I developed with Ralph, he decided to adopt me as his apprentice, and he was going to teach me field physics or kill me trying. And so for more than 10 years, Ralph's patient tutelage, he finally got me to start thinking in 3 dimensions and thinking about energy the way it was properly defined by physics. It's electromagnetic field traveling in a dielectric, and that became a change in my whole career. Once I started understanding what Ralph was teaching me and applying it to both my products and those of my customers, I went from being confused and hopeful to absolutely confident in the designs. And when my customers use the suggestions that I provide based on Ralph's rules, I'll call it, with 100% success. And with all the products that I develop for NXP, because I have a small tools operation that does the impossible and the unexpected types of tools that nobody else wants to or can, with 100% success as well. My systems always pass EMC. We do it without any hand waving or praying, because the rules are simple and the behaviors of the fields are predictable. And that's where I'm at today. I'm a technical director with NXP because of Ralph's patience with me and teaching me fields. I think that if I hadn't found that magic key, that, I have 42 years at NXP right now. So I would probably have retired because I had run out of things to do, and I wasn't able to affect change in both NXP and in the industry. Now I'm on a mission to take Ralph's legacy, because he passed away in 2019 at the age of 94. So he contributed a long time of his life trying to teach people about fields, to pass that knowledge on to the world. And that's my mission. And that's why I'm really excited that you've given me this opportunity to talk about energy management from Ralph's perspective.
It's great to have you here on the show. I like what you said in the essence of the last 5 minutes of what you just said. And the biggest thing is getting the proper mentorship that Ralph provided to you that guided you early in your career and has created this beast of a designer, if you don't mind me using that term beast, but that you were truly a master of your domain and your evolution. And, when I see you at the different trade shows, such as PCB West, PCB East, when you're speaking and you're passing on, that knowledge or that mentorship that Ralph passed on to you, it's amazing to see that. And it's amazing, I remember early on back in the day when I sat in your classroom for the first time and I listened to your lectures and I gobbled that stuff up. And you, Rick, and Susie, and many other industry icons out there that are doing their magic and passing that knowledge on and trying to pay it forward. So that way our industry continues to evolve like it does. Keep it up. There's a lot of us out there that are following along and trying to absorb these industry best practices, which you're passing on. So let's get right into it. So tell me, what kinds of problems can occur when a board is not designed for power integrity?
That's a good starting point because, like I said at the beginning, the power distribution system is the foundation of the functionality of any type of electronic control system. It's really important. It's the most critical of all the nets on the board. If you have a problem with the power distribution system, you can't fix it on the output side. You can't get rid of noise in the signals. You can't get rid of noise on the board without first addressing the power supply design. And that there are a couple of issues that are specifically attributed to poor power supply design. One is the obvious one: things don't work, whether it be just powering it up at room temperature and you have problems with functionality. The data bus doesn't work, or your driver for your motor doesn't work. And those kinds of things are pretty obvious, but often are tied to poor power design. The other side would be from the perspective of failing electromagnetic compliance. Almost all of the radiated emissions issues that I've looked at as a signal integrity specialist have been directly associated with the input power structure from the connector to the IC. And you see issues with the sourcing of energy to the transistors in the IC. When you turn on a switch, if it switches in a nanosecond, you have a wave of energy driving into the transmission line on the outputs of the device at, it's a gigahertz signal. When you do that, you have an energy flowing out, but that causes a depletion in the field that's stored upstream from the switch. That also is a nanosecond event. So you've got a gigahertz depletion wave, I call it. That's where you have a drop in voltage because you're pushing energy out the other side, and there's an impedance mismatch. So there's not enough energy in that pipeline to deliver the energy to the switch adequately. The analogy I use is if you're in the shower and somebody flushes the toilet, the cold water doesn't have the capacity to supply both the shower and the toilet, and you get a drop in the amount of cold water being delivered to the shower, and you get scalded. The same thing happens with fields. It really behaves quite like water in pipes. So when you turn on the switch and you start things going, that depletion wave will travel at the speed of light the same time that you have the energy going out of the switch. And if there is not a source of energy within what Rick suggests, a 20th wavelength of that switching event, then if you approach the quarter wavelength of transmission line, you start to see opportunities for radiated emission that are consistent with that wavefront. So if you have a nanosecond depletion wave, you have a gigahertz signal looking for an antenna. And that's something you're going to see then at a clock period. So if your switching event is the core switching, and you have a clock at 400 megahertz or whatever it is, then every clock period you will see a burst of energy at a gigahertz. So you have this multiple event happening, and that is the other thing that happens is poor power supply design. So you have to have a good transmission line, meaning that the power conductor is one dielectric away from ground. The first storage component of energy, the first capacitor, needs to be within that magic 20th wavelength of the switching speed of the driver. And then you have to make sure that the feeding network from the connector power supply has an adequate amount of capacity, meaning it's impedance, not resistance, not inductance, none of that stuff matters. The characteristics of the transmission line are such that you can deliver the amount of field energy to support this event. That is looking at current from the proper perspective. Electromagnetic current, an ampere, is a coulomb of electromagnetic field moving past and through a space in a second. So you need to have the plumbing to support that type of energy. If you need 5 amps, you're going to need to have impedance that allows you to deliver 5 coulombs of energy per second.
I cannot stress that how the basic foundation of your stack up, of getting the basics so that way you can control your energy, is amazing how many people get it wrong.
Absolutely. The stack up is the foundation of the PCB. And so many app notes ignore the need for power to be next to the ground plane. One of the problems with that is that when you use most simulation tools and you don't use them properly, you can put in your design and you can tell it where the power is and you can tell it where ground is. It doesn't know or care if it's next to ground. And any of the subsequent layers between the power supply and the ground plane, it ignores them. So you can't tell that you have a bad power distribution system. And people focus on the resistance of the copper. And the way you can make the simulation tool happy is you can go to heavier weight copper for the power because that reduces the resistance. That doesn't change the impedance of the transmission line. It's like if I have a 1 gallon a minute hose and I need 5 gallons a minute, and I decide, well, I'm going to make the hose out of steel. It's still the same diameter hose. I still only get 1 gallon a minute through the hose. If our traditional perspective is to throw copper weight, I need more current, so I'm going to go to from half ounce to 2 ounce copper. Doesn't change the characteristics of the dielectric. And that's where the energy flows.
You talked about traditional approach. That leads me to my next question is, can you discuss the traditional approach that's been going on even today with the designing of PDNs and your perspective on that?
One of them is that they typically do not ensure the transmission line integrity. And that's the first rule you must follow. So there's no guidelines in most cases that tell you that the power conductor must be next to the ground plane. The second is they look at power supply design from a circuit theory perspective. And all the discussions that I get involved in, they want to argue about the return path, the return current, the current loops. That is not what's happening. The energy goes from where it is stored to where you tell it to go, hopefully. That's a one-way trip. The energy doesn't go back to the power supply. The field travels in the dielectric. It goes from source, where the voltage is higher, to the load, where there's a need for field, and it moves serially through that space. So the idea of minimizing inductance and minimizing loop area has nothing to do with reality in this case. What is important is good transmission line design, meaning that it's intact. Ground has to be next to power. The next thing is that the first source of energy needs to be within that magic 20th wavelength. The most important thing in power supply design is how far it has to go to get that first bucket of energy. And it's all done by waves. There is no such thing as DC. It's always waves, whether or not they're very low frequency or they're very high frequency because you're supplying cores. The energy is still moving in waves. So you get a depletion wave that goes someplace and brings energy back. The first order depletion waves are a factor based on the switching speed of the transistor that you're working with. That very fast event, which has got a very high DVDT, because you've got not a lot of energy stored in the transmission line connecting the IC to the capacitor, is going to be a big drop, a high frequency. It's going to come to the first capacitor. That's where even Dr. Hubing says you want to use the smallest capacitor in package that you can based on your manufacturing requirements. It goes to that first node, brings energy out of it. Because there's so much energy stored in a capacitor, the percentage of field drop, your voltage drop, as a result of pulling energy out of the capacitor is very small, 1 or 2%, maybe a little more, because it's limited by the transmission line connecting that cap to the switch. The good news is at that point, the depletion wave is no longer a function of the transistor. It's a function of the geometry of the capacitor. So you get a lower frequency event with a lower drop in voltage that then goes upstream into the power supply looking for more energy. Now the 20th wavelength is significantly larger than the 20th wavelength coming out of the IC. It goes to another capacitor, typically a larger package with a lot more storage, and you take an even smaller amount of energy out of that cap. So you get a lower drop, and then that resulting depletion wave goes upstream farther and looks for more energy. And I design my power supplies in that perspective. First order is transistor based, then the rest of them I'm based on, where can I put these different charge wells to supply each other. By the time it gets to the power supply and the connector, I'm at pseudo DC because I'm not trying to supply energy for very fast events. You're not going to get a nanosecond energy source from a capacitor that's 3 inches away. And then I just make sure that the capacity of these interfaces, the transmission lines that connect the different nodes, matches the amount of energy that I'm requiring. And if I'm trying to supply a lot of pins to a BGA, I use a power island. I never use planes adjacent to a ground plane, and then I connect those in the Z-axis properly to the pins on the IC. If I need a whole lot of energy, like I did for the network control board I did a couple of years ago, the slew rate for the core supply was 7 amps per microsecond. I ended up, in order to deliver the correct amount of energy, put 4 different dielectrics where I had power, ground, power, power, ground, power. So in parallel, I have 4 separate dielectrics that present energy to the capacitors, which are mounted directly beneath the BGA. And then those capacitors there were like 100 pairs of power and ground pins going up into the core, then could provide energy. And then the routing from the output of the PMIC and there's local capacitors that feed these power islands that are close. And then I use a low impedance. There were 3 dielectrics connecting the PMIC to the local charge well, which is the big 10 mics, an array of those that then supplied the very small 0201s in that case. And in that design, the reference design had 26 ferrites and inductors in it. And I don't believe in restricting energy flow. And that's what we had done in the past. I was taught that in the very beginning. You put ferrites and inductors in series because you want to starve the switch, because we believe that the EMC issues were a result of the output. They were not. They were because we were not feeding the switch properly. So you see in these IC design guidelines, I got 3 or 4 1.2 volt supplies, and they isolate them with a ferrite, but they're all 1.2 volts. So I don't isolate them. I put them together. I let them all feed on the same energy source, because the beauty is that every single power ground pair, the depletion waves coming from the IC die itself, they're asynchronous. They happen at different times because of the distance they have to travel. Even the femtosecond differences are going to make it so that you're pulling energy out at different times from this array. And then the other beauty is, if you use a power island, is that impedance, that space there integrates those signals a bit, because it takes all of the capacitors and then they all see these various depletion waves. And so it just ends up being a kind of a bucket brigade, but each one of them happens at a different time. And then your job then is just to make sure that the connections to these sources of energy all the way back to the PMIC itself have, again, the capacity to deliver that energy.
Understanding the basic fundamentals of PCB layout is key. And what you're describing is the foundation of how that board is going to perform with controlling the energy in that stack up. You did a lot, in the past regarding sharing this knowledge. And it leads me to my next question of how you're continuing this effort to educate the industry. In your published article in PCDNF in January of 22 edition, can you briefly explain the $1 billion mistake? I love when you go into that. And can you share with our audience that $1 billion mistake?
That article came out of a request from the IEEE EMC Compo that was going to happen. It was an international event that became virtual because of the COVID events. And so I want to talk about what's happening in the industry and why I think that we have all these problems, because it became a fundamental perspective that I think I've figured out. They decided that I didn't need to do that because it wasn't scientific enough. So I went to Mike Butow at PCB. I said, Mike, would you think this article would be worthwhile? And he's like, oh, yes. So I put together the $1 billion mistake perspective. And then Wonder of Wonders, Mike put it in as the cover article. So I was very, very pleased with that. And just one note is that I've received zero negative pushback on that article. And then not long after Mike had agreed to publish it, the IEEE came back to me and said, could you please present this to the Compo? And I presented it to an audience that was primarily academics, and we had this discussion. So the foundation of the $1 billion mistake is the perception that we are taught about circuit theory and current flowing in a loop. And the basic idea, and that's my perspective for most of my career, was electrons and wires and current flowing in a loop. And I tracked it down to the diagram everybody's seen with the battery on one side and a switch and a light bulb on the other side. And they show the arrow on the top going from the battery through the switch to the load, and then the arrow pointing going back the other way. That whole perspective is what has become the basis of everybody's design philosophy forever. And it didn't hurt things in the beginning because the geometries of the switches we were dealing with in the beginning of my career were so large relative to the physical size of the circuits that everything was always lumped. So you could do stupid things and it didn't make it break. So we decided that we were doing the right stuff, and all the guidelines were evolved over time, not by deciding to what the right thing to do was. We decided what didn't make it break at the time. And as we continued down the technology path, this is where it started to become a problem. When I moved to Detroit in 1987, they were making the change from HMOS to HCMOS. And I was certainly not an expert in EMC or signal integrity at the time. And I'm calling on my automotive customers, and every module's failing EMC. And we did this before. It worked before we went to these new ICs, and it didn't work. The thing that happened was the geometry of the HCMOS was about 10 times smaller. The switches are 10 times faster, which means that the antenna size is 10 times smaller. It's all ratiometric. That's the beauty. The only math you need now is algebra. We went from where a radiating antenna needed to be basically 30 feet long. So if you weren't working on a tractor trailer truck, a bus, or a train, you didn't have any structures that were long enough to be radiating antennas. When we moved to the HCMOS, and this is something that came out of my creating my first presentation, the antenna now is 3 feet long. And what's hooked to every single automotive module? A wiring harness that's at least 3 feet long. So we hooked a radio transmitter up to an antenna, and we couldn't figure out why we were having problems. And looking back, I feel really, it's the Homer Simpson beer can smashing moment. I feel really dumb that I accepted the idea, and this is where circuit theory really falls apart. We all believe in radio. Radio is electromagnetic field energy, and it travels through space. For some reason, when we take that same energy, electromagnetic field, and put it on a circuit board, it changes from electromagnetic field to electrons moving in wires or holes, whichever side of the bus you want to be on. And we accepted that perspective. That explained what, it worked. The perspective worked until we moved into smaller geometries. And then things stopped working. And we're like, well, we don't know why it doesn't work, but because we don't even have a clue what we're doing for a living, which is the billion-dollar mistake, is that good teams of engineers continually are faced with using guidelines that are based on what didn't make it fail. And the results are that they fail EMC. Most of my customers will tell me that it's 3 to 5 cycles. So billions of dollars are these wasted dollars on people who keep redoing the same design with the same guidelines and not going back to figure out what is the fundamental problem here. And it's traced all the way back to the universities, and they don't connect the field theory and the science to their circuit classes. So everybody takes a couple of classes in fields and they hate it because the math is heavy and it's boring and you got more homework than you want to deal with. And so when they get back to circuits and into their careers, it's the easy stuff. And it's reinforced by the guidelines and the senior engineering teams at all the companies. And we keep redoing things wrong on purpose. And the cost of the industry in time, companies go out of business all the time now because they can't make the window for their product. And companies, they stop product development because they can't afford these iterative cycles. And the cost, especially during the post-pandemic years when supplies were a problem, you may not be able to get parts to build your next rev or the next rev. And all that costs money, and it comes right off the bottom line. This is money that you are taking away from your stockholders. This is a problem. And I think $1 billion is probably a very, very conservative perspective. It's probably tens of billions of dollars that in cost, designing things you're pretty sure are going to fail. And then when they do the next version, it's a hope and a prayer. They don't know that it's fixed. They make a couple of small changes, beg to get parts and get expedited assembly, and then beg for time in the chamber with no idea whether it's going to pass or not. The foundation is that the consumers of engineer, the companies who hire them, are not going back to the universities and saying, hey, we need to change the skill set. Our engineers are coming out without a good understanding of the nature of their industry. And until somebody goes to them and tells them that, they're happy, they're selling their product. People are buying their product. There's no reason to change. If they have to change the curriculum, there's even more resistance to that because the professors that wrote the textbooks are not going to be the ones that write the books for the new curriculum. And they don't want to have that happen because they don't want to kill that revenue stream either. So again, if there's no reason for me to sell any car that's not black, then I'm not going to make them green and red. I'm going to continue to sell black cars. So the challenge is for engineering companies, the big ones, Ford, GM, General Electric, and XP, to go back to the engineering schools and say, hey, please, let's update this skill set. Right now, the only 3 places that I'm aware of that have a good curriculum that's connecting the dots between field science and circuit theory is the Missouri Technical University, where Todd Ewing was a researcher and Dr. Duniak. They connect the dots. They do research on behaviors of fields, materials. So Todd went to Clemson as the endowed chair of the Michelin Automotive Technology Center. Todd brought his expertise to Clemson. So Clemson got added to my list. And then I found that Grand Valley State University in Western Michigan is working with a consulting firm. They're graduates from Missouri Tech. So they connected the dots between them. Beyond that, I haven't been able to add anything to that list. So anybody going to a traditional engineering school is going to get a very small exposure to field science with no firm direction that this is how things work. And that's the $1 billion mistake.
I'm chomping at the bit as you're talking about this, especially in regards to universities and education. And that's a whole nother topic that we'll keep for another time. But the bottom line is when it comes to PCB layout or designing circuit boards, in my opinion, the universities are failing in having curriculums in place to set up engineers graduating to come out for success, because by the time they hit the field, they're clueless in regards to how to design a board correctly, if they even know how to design a circuit board.
And then the guidelines that are being published by IC vendors and by companies that they use are based on lore and what worked 10 years ago. And they don't go back and correct them because they don't tie the two pieces of data together. It failed EMC for this reason, whether it would be radiated emissions, and they don't go back and see where in the design that didn't work and then adjust the guidelines accordingly. That's the thing that we have to try to do, is to do that. And in the classes that I've taught with academics in them, they all agreed that that should happen, but there's just no way they're going to be allowed to do that. Even when they try to teach the fields first and then follow with the circuit theory, that it doesn't happen, that they still are going to present the circuit theory first, because it's all about, how many seats can you fill? If they want to have engineers, they all take these classes, they like them, they just accept the burden of having to go struggle with a fields class, and then they get through that and get on the other side, and then they don't have to do it anymore, and they get to their jobs, and they're being told to do the same thing they were taught in school, current loops, electrons and wires. And that just gets back to the idea. Electromagnetic field, everybody acknowledges, travels at the speed of light. Matter cannot travel at the speed of light. Electrons have mass, therefore they cannot travel at the speed of light. So how are they involved in the energy at all? It's like the wake of the boat. The electrons do move. There is certainly displacement current, but it's not the energy movement. The energy movement is, again, the field and the dielectric. It's the Mino field that's bullying these poor electrons to move from valence layer to valence layer. And that whole event is the secondary effect of the field moving through.
You talked about the EMC requirements. There's been a steady increase in failure to pass EMC requirements as IC geometries grow smaller and switching frequencies increase. Why is this happening?
One is the smaller geometries are driven by a couple of factors. One is cost, as our customers are asking us for lower cost, and you shrink the transistor size, you can get more die per wafer and you can reduce the cost. And higher performance. You want to have the clocks go faster and you want these things to go faster. But we have to change the rules, or what that does is what we talked about, that the chances of failure are reduced by the scale. It's a direct inversion. The faster the frequency, the more likely you're going to have problems at higher frequencies. And one other factor is that as we've increased the number of radio sources where you need radiated emissions to do the work, that they have extended the spectrum for compliance to higher frequencies and lower frequencies with higher levels of immunity required and lower levels of radiated emissions allowed. So we've got ICs that are going in one direction where they're better at making noise and easier to disturb, and putting them in environments where they're not allowed to make any noise and they're being hammered by higher energy levels. So that, on top of the fact that the fact that we aren't taught properly, ends up with designs that are just destined to fail. And it's going to only get worse as we continue to add more and more, especially in automotive, more and more sources of energy. They're adding more and more radios in the vehicle, and all of those increase the amount of immunity that's going to be required, but we're still going down the shrink path. I'm working with a product now, the new S32N parts. They're 5 nanometers. Those transistors are switching in femtoseconds. And for the power supply side, these things they're 40 watts. And it's only going to get worse. They're doing 2 nanometer transistors now. They're looking at 1. They're looking at sub-nanometer. Unbelievable what's happening. One more is that the problem has moved from being just on the circuit board into the design of the IC itself, not just the interposers, but the die itself. You're going to have energy sources properly placed on the die, because the distances on the die relative to the switching speed of these transistors are now big enough to have a problem. And the IC designers have They've been in lump land forever, and they think they don't have to deal with it. They don't approach the problem properly. One of the examples I use is, have you ever heard of a processor normally clocked faster than 4 gigahertz? It doesn't happen. They went to dual cores, quad cores, 16 cores, 64 cores as they went down the shrink path. They still can't clock it any faster because they don't design the power distribution system properly. And when you don't do that, one of the results is not just that you get problems with delivering the energy properly, but you increase the amount of conversion of electromagnetic field to kinetic energy. Because every time the wave moves, it's pushing around the molecules of the boundary layers, the conductors. That conversion from electro energy to kinetic energy is heat. So they can't get the heat out. And the way you get the heat out is by not having it. So again, back to the idea of a good power distribution network, one of the other failures is the IR drop stuff that everybody worries about. I don't care about IR drop because my transmission lines have the impedance that matches the energy delivery. And the issue there is back to the displacement current in the displacement current density per square centimeter. So the higher the impedance, the more waves it takes to deliver the energy. And again, you've got usually a smaller surface area that the wave is seeing. So the displacement current density on a 10 mil trace is higher than that on a 20 mil trace as far as width. And by doing the proper impedance, you don't see issues with IR drop. When you design a resistance, and this is back to the specs of the IC, they talk about requiring 250 milliohms of impedance for power supplies. That is not an impedance factor. To get 250 milliohms of impedance requires, I think it's a 1 inch wide trace with a 1 mil dielectric. It's not going to happen. They're talking about resistance. And the way you meet the impedance targets, again, is to go back to adding thickness to the copper for power. Problem with that I see is if that was the right solution, why are we not doing anything with the ground copper? They're both involved. If it's return current, it's the same current going with both ways. If you're thinking about this idea of current and wires, then why don't you change both of them? It's like having two 18-gauge wires and you need 50 amps. Well, I'm going to make one of these wires, the power wires, now as a double-aught cable, but I haven't changed the return and I haven't changed the space. So what's going to happen? I'm still going to burn one of the wires to a crisp. Again, because that's the conversion of the electromagnetic energy into kinetic energy, which is the heat. And that's the fundamental problem.
I see the issues only getting worse. You add the complexities of the packages, the complexity of the overall electronic systems that we're trying to design. You compound that with the lack of education or the know-how coming out of the university of the young engineers who are now being forced to do layout that have never even touched the layout. You just have the perfect storm happening. And then you have older generation designers like yourself and myself and many others who are soon to be retiring. And so you have this void or this gap in the industry getting bigger and bigger, and it's just going to get worse. When you talk about rules in designing, for those who don't know, can you explain the rule of triplets to our audience?
Triplets are my favorite structure, and this came from my understanding from Ralph. And part of my challenge working with Ralph was he was a physicist, so he spoke in very high level, big words, and he loved math. He could spend all day talking about Maxwell's equations and converting that to mortal speak so that normal people could understand it. And that is where I started looking for diagrams that I could use. The beauty of a triplet is that if you have a signal and then a ground and then a signal, that forms what I call a triplet. There are three conductive elements in that stack. The signal to ground on the first layer is a dielectric that's intact. And then the ground to the signal is another dielectric that's intact. So if you don't have ground planes, you could put traces for signals on each side of a ground trace, and then you still have a transmission line where each signal is one dielectric away from ground. So by using just three conductors, I've created two pretty good transmission lines. In the case of a board stack, if you have signal, ground, signal, That triplet is really powerful because when you route from layer 1 to layer 3, the hole around the signal via connects the dielectric in the 1 to 2 to the dielectric between 2 and 3. So you automatically have the dielectrics paired together. So they're a mated pair of dielectrics when you route from 1 to 3. So in my favorite board stacks, they're even numbers of 3. So 6, 12, 18. Anytime you go outside of that even number of 3, like going to a 4-layer board, which is probably the most popular board stack in the world, 1 to 3 are wonderful. They are automatically good transmission lines. You route from 1 to 3, they are automatically coupled so that you got the transmission line in the horizontal dielectric connected in the z-axis to the next horizontal dielectric. Layer 4, contrary to popular belief, is not returning, to use that horrible word, on layer 2. There are 2 dielectric layers and a copper layer between 4 and ground. So layer 4 is an orphan. The only way you can do a good job on 4 is with the coplanar ground, and that's where coplanar triplets are helpful. And the ground can be, and usually should be, ground flood. But when I route from 1 or 3 to layer 4, I have to make sure that there's a ground transition via to make that vertical pipe to connect dielectrics between 1 and 2 or 2 or 3 to the dielectric in between the copper on layer 4, because it's the coplanar dielectric that you're using. And that's very, very important for doing that. And the whole idea of having the vertical pipelines is just like if I've got a water pipe in the basement and I need water to go to the upstairs and I don't put a pipe there and I turn the water on, it's going to get upstairs eventually, but you're not going to like what happens. The same thing happens with the fields. The fields will find their way there eventually, but it's going to spread out all over the place, and you're going to end up with problems first in the number of wave cycles it takes because the impedance is so large. So your bucket's really small, and it's going to interfere with every other signal in that space. Every time one of those waves hits a conductor, it's going to cause crosstalk, it's going to dilute and affect the signals in that space. So that's where triplets are really powerful. And my favorite board stack is the 6-layer, because then I've got ground on 2 and 5. I've got 2 triplets in the board stack. And then my only challenge is to make sure that when I go from the top triplet to the bottom triplet, I put a ground transition via there so that I have my vertical pipe.
Yeah, exactly. And I think there's a lot of places, a lot of areas where designers get it wrong is they miss that transition via on that z-axis. They forget all about it, or they don't know what they don't know.
I've had boards fail functionality for the lack of one ground transition via, and I've had a number of boards that failed EMC because of one missing ground transition.
We're running close on time here, so I got one more last question I got to ask you. How would you recommend the new generation to get educated, especially when it comes to power integrity and power distribution networks regarding PCB design?
Well, you have to seek the knowledge. You're not going to get it in the university. It's just the same thing that you and I have done. We've gone out to look for it, and it's really hard to get books. I mean, it can give you a list of textbooks that people have written. You know, Ralph has 11 books. All of them are based on the science, but it's hard to get that from. So really you have to seek it out in ways you can understand. That's why I try to make sure that all of my classes are available on the web. I've been working with Professor Obeng in Ghana. He's created this PC Africa YouTube channel. And everything I've ever created, Eric and I have gotten together and I recorded it and put it on his channel. So that's there. I try to publish as much as I can. I go to PCB East, PCB West, I go to DesignCon to try to make sure that I'm current on the science and the materials, because one of the things that they don't tell you is you really have to know about the materials. What is the copper capable of? We've mentioned HDI in the past and Ultra HDI. You need to know what technologies are there and then take that knowledge of dielectrics and transmission lines, the plumbing for the energy movement, and apply those together in order to be successful in your design.
Exactly. You got to know the fabrics. I mean, from your ICs to your board to the overall system, you got to know the fabrics. Nowadays, with model-based engineering approach, you get into the digital twin, you've got to do your due diligence and you got to understand it and to get that education.
it's difficult because the tools just are not complex enough, let's put it that way, to be able to analyze properly the full three-dimensional structure of a printed circuit board, and then the ICs on top of that. And you really have to seek out the knowledge. It's frustrating because we're still not teaching it correctly. And the new engineers, even if they have grasped the concepts properly in school, they still are not. And this is where I was at in the beginning when I first started learning the reality. I didn't feel confident enough to argue or to go against the rules that people were presenting. And I have had the students from my classes, when I see them again in another year, said, they just weren't comfortable enough and understanding the rules to go back and try to push for change within their companies. And it's going to take all of us, the senior people, to try to create better guidelines and to make these trainings available. One thing that I would suggest is that I was able to capture Ralph in the only videoed sessions that he allowed of him teaching his final book. So those are available. It's pay-per-view. I'm glad to say, because it's ralphmorrison.com. For $50, you can get access to 3 2-hour sessions of Ralph teaching his last book, Fast Circuit Boards. The proceeds go to his widow. So this isn't a money-making thing for me. This is where I can have his wife be able to take some recompense for Ralph's dedication, because he really never got much money for his books, even though I think he sold over 2 million copies over his lifetime of his various books. But the return on that investment was very small. And he said until I met him and started working with him, that nobody ever really listened to him. Again, my mission is driven by the fact that he was so patient and he was so right, that I want to show everybody else. This stuff is not rocket science. It's really simple. 3-dimensional structures. The geometries are what drive everything. The geometry of the switches, the geometry of the transmission lines, and it's all ratiometric. You don't need calculus. You just need to know if this thing is 10 times faster, the rest of the geometry is 10 times smaller.
As things get more and more complex in our industry, the bottom line is it all comes down to getting the basic foundation correct. If you don't have that correct, everything's going to fall through. And that's what it comes down to. The majority of mistakes are made at the rudimentary basic level. This is great, Dan. I think that's all we have time for today. I want to thank you again for sharing your insights on power integrity and design, passing on Ralph Morrison's legacy. To our audience, please continue to tune in as we talk more trends, challenges, and opportunities across the printed circuit industry.